Welcome to the first lecture for our course in Advanced Algebra and Geometry, and this will be about compass and straight edge constructions, and we'll start with the very basics of geometry. Okay, so what is a point? It's kind of hard to say, honestly. In the context of Cartesian coordinates, okay, where you assign numbers to a pair of numbers to every point in the plane, then it's really easy to describe by a pair of real numbers, x, y. Okay? So that's if we're talking about Cartesian coordinates. But in terms, if you go back to the writings of the Greeks and look what they thought about points, they considered it a location without length or breadth. Okay, so it kind of it's a thing, but it's somewhere, but it doesn't have any substance in itself. It's specifying a location. Okay. For our purposes, it's okay not to have a great definition. Okay, so logicians will say it's a primitive concept. So can't really define it in terms of more basic things. It's kind of one of the most basic things you can have. Okay. And we can say something similar about a line. Okay? In Cartesian coordinates, this is easy. It's the set of all points satisfying an equation, an equation of the form ax plus by equals c, where a and b are, let me write it like this, a and b are real numbers, not both 0, and c is also a real number. Okay. And let's make sure we specify this xy satisfying an equation of the form ax plus by equals c. Okay, so that's for Cartesian coordinates. So it's clear why we can enjoy ourselves when we're talking about objects in the Cartesian plane. It's very easy to define them. But similarly to this, the Greeks considered it an object with length. And in general, since we're talking about lines, this is infinite length, but no breadth. Okay, so there's no second dimension there, it's just all one dimension. Okay, and similarly, this is a primitive concept. In terms of how points and lines are related, so two distinct points define a unique line that contains them. Okay, this is, we're in the Euclidean setting. Okay, in other versions of geometry that might not be the case, but two distinct points define a unique line that contains them, and two lines are either parallel, okay, and we'll talk about, let's hold off on defining that actually. So two lines, if they intersect in one point, okay? Okay, so obviously you could have the same line twice that intersects in a lot more than one point, but two lines that are actually distinct will intersect in one point. Okay, so that's a lot of words about points and lines. a line segment is a piece of a line. So we've specified that a line has infinite length. So a line segment is a piece of a line of finite length. It has 2 points as its boundary. Okay, so that you're describing basically all points on the line between A and B. Okay, so if you have points A and B, then the line connecting them will be denoted by AB, and this is a line segment. As for a ray, this can be thought of as a half of a line. So all points on a line to one side of some fixed point. Okay, so if you have a line, let's say you have a line L, okay, then you can fix some point P, and then everything on this side of P will be your ray. Okay, so this is a ray. Okay. And if you have, let's say we wanted to fix an extra point here, Q, and then we could denote this by PQ with a single arrow pointing towards the Q to indicate that P is the boundary and it goes towards Q. Okay, so that gives us line segments and rays. Now let's describe circles. So again, when we have Cartesian coordinates, this is pretty straightforward. This is the set of all points x, y, satisfying the following equation. X minus h squared plus y minus k squared equals r squared. Okay, and for this to work, we just need the, where h and k are real numbers, and r is a real number greater than 0. Okay, and it's not so important that it's greater than 0, just that it's not equal to 0. If it's less than 0, you just get squared, and so you're looking at the positive version. Okay, but that's just in Cartesian coordinates, but the Greeks didn't use Cartesian coordinates. Right? They're named after Descartes, who was French, and that's after the Greeks. So what did the Greeks do? Well, they described a circle as all points a fixed distance from a fixed point. Okay, so in the equation that we just wrote, this is all points a distance r from the point hk. Okay, we can draw a figure to illustrate this. So if we have a circle, let's make this blue. Okay, hopefully that's roughly circular. And we have this point, which is roughly in the middle. Let's call that P. Okay, then if we choose points on the circle itself, okay, we would expect that this line segment and this line segment are equal. Okay, and they will have length r. Okay, so PQ should be, the length of PQ should be equal to the length of PR. Okay, and that defines a circle. It's all of the points like Q and R that would satisfy that equation. Okay, now let's talk about angles. So angles are defined as a pair of rays with the same, originating from the same point. Okay. And we assign a measure to the angle. And these come in degrees or radians, or your favorite alternative to those. This specifies what portion of a circle would be confined between the two rays. Okay, so let's give an example of that. So let's say we have our point P. Let's use blue. I like blue. Okay, so we're going to draw the circle first because it's always hard to draw a circle around a point. So okay, so this is our point P, and we're going to say that our rays are originating there. Okay, so we have first ray, second ray. Okay, so the angle, this measurement, is describing what portion of this circle is between the two rays. So if the circle is said to have circumference 2 pi, then the angle has measure equal to length of enclosed arc in radians. Okay, so if you have the whole circle in your angle, that would mean an angle of size 2 pi. If you have half the circle, that would enclose a semicircle, so that would be pi, and that would tell you that your angle has pi radians. If you have a quarter circle, that would be 2 pi divided by 4, or pi over 2, and that would tell you that you're looking at an angle of pi over 4, pi over 2. If you're doing things in degrees, then just take 360 degrees as the distance around the circle and take the proportion of the fraction of the circle times 360 degrees. Okay, so what is a right angle? A right angle is exactly 1/4 of a circle. An acute angle, of course, is an angle corresponding to less than 1/4 of a circle. And an obtuse angle corresponds to more than 1/4 circle. Okay, and we'll draw some pictures. Okay, so start with a right angle. This corresponds to exactly 90 degrees, 1/4 circle. And then we can do a nice acute angle. So something like that. This is acute. And then we would have, let's give it brown. So something like this would be obtuse. Okay. And I'm sure none of this is surprising. This is usually covered in the middle school or high school curriculum, but since we're making the exercise of building things up like the Greeks, we're taking it from square one. Okay. Now we talk about parallel lines and perpendicular lines. So parallel lines are one of the more controversial aspects of Euclidean geometry. And if two lines do not meet at any point, then they are said to be parallel. Okay. There are versions of geometry where every pair of lines intersects. Okay, so the idea that there is such a thing as parallel lines is something that Euclid has to assert as a postulate rather than as some kind of provable geometric fact. Okay, and here we can take two lines. Okay, if they will never meet, then they are parallel. In terms of Cartesian coordinates, these are the lines with the same slope. They're also pairs of vertical lines. Okay, since vertical lines, you can't really define slope in quite the same way, so we'll assert that any pair of vertical lines are parallel, but for other lines, if they have the same slope, then they are parallel, unless they are identical. So they're either identical or parallel. Okay. Perpendicular lines are lines that meet at right angles, i.e. if you take any pair of rays, one from each of the two lines, then they'll give you a right angle. Okay, we can draw one of those. Okay, you can see that this is a right angle, right angle, right angle, right angle. Okay. Triangles. So a triangle is a figure which contains 3 points and all 3 line segments connecting them. Okay, so for example, we'll have these 3 lines and these 3 points. So this is P, Q, and R. So then the triangle is the figure including these points and the three line segments PQ, PR, and QR. Okay, and these are important from perspective geometry because these are the first objects, or the simplest objects that you can describe that have area. Because if you try to define anything with just 2 points, that's not going to have area. 2 points define a line, so they do not enclose any area, or really define a line segment. Whereas a triangle has 3 points which enclose area. Okay. Moving right along. What does it mean for 2 triangles to be congruent? 2 triangles are congruent if they have the same size and shape. Okay. Equivalently, you can move one triangle into the other without stretching or manipulating it, stretching it, or breaking it. Okay. And so for example, if I have, let's draw a triangle. Okay, so if I wanted to take this triangle and put it over here, these triangles are still congruent since all I did was copy and paste. It's the same shape, same size, and I could just move it back over here and it would occupy the same position as the original triangle. Okay. I could also rotate this. Let me see if I know how to rotate. Oh, here we go. Could also rotate this, and this is also congruent to that original triangle. Okay, because I can just rotate it and put it back in its original spot, and it will occupy the space of the original triangle. So these are all congruent triangles. Okay. You might remember this from high school. SSS is the side-side-side rule. Okay, and the idea here is if two triangles have the same side lengths, and since it's three sides, it's the same three side lengths, so all of the side lengths are determined, then they are congruent. Okay, so how does that work? Well, let's take, this time we'll make 3 different color boundaries. So let's say we have these 3 different side lengths, and then I give you another triangle and I say, you know what? This is going to be the same 3 side lengths, but maybe it'll be different. So here's how I know that it has to be the same. Well, the red edge, I'm saying, okay, let's start with this red edge. I haven't done anything, I haven't made any choices yet. So this is not a, I'm not placing any constraints that aren't there already, right? This is not specified. Okay, so now I'm placing an edge here, but let's say I don't know for sure that this is the right angle to place it at. So I know that it's the right edge length, so I'll take every possible placement of the triangle that has that length. So the way I'm going to do that is by drawing a circle whose center is here. Oh, I hate this. Okay, one second. No, this is still bad. Okay, let's see if I can do this reasonably. Okay, so a circle whose center is here, and whose center is at the corner there, and whose boundary includes the end of that edge, that blue edge. Okay, so now I don't know that the blue edge has to occupy the position that I said it would occupy, but I do know that it has to end somewhere on this circle if it has that length. Okay, similarly, I can do this with the green edge. So I'm going to say I don't know for sure that this green edge occupies this particular space, but I do know that it has to live somewhere on this circle, and this circle is maybe a little funny. I need to make this a bit bigger and put this here-ish. Really, this should be here. Okay, thereabouts. Okay, but now, even though I'm not making any choice about where those 2 edges live, I've basically decided that the third point that hasn't been drawn yet must be at one of these 2 spots. And if it's at either of those two spots, then the triangle will be either the triangle we started with or its reflection. Okay, so that's how side, side, side determines the triangle we're talking about. Okay. Okay, now we have side angle side, and it's a similar idea. So if we know a specific angle and then the length of the two segments on either side of that angle, then the triangle is fixed. Okay? And it's straightforward because you know what the angle looks like. It's going to be, so if you know the angle, you can just draw that, and it'll be something like this and this. Okay, and then knowing the length tells you where to cut this line, and then that tells you where the remaining edge has to be. Just at the end of the blue line meeting up with the end of the green line. That determines your triangle. Okay. Finally, we have angle side angle. And it's the same idea here, where you're kind of forced by the constraints that you're setting to specify a specific triangle. So you have specified the length of a side as well as the angles where the other two sides meet that side. Okay? So if we have this side length, and then we know that we have an angle that looks like this over here and an angle that looks like this over here, then in order for that to be a triangle, there's only one place for the remaining point to be, and that's right here. Okay, so we'll have our points here, here, and here. Okay, so that's all about congruence of triangles. Similarity of triangles is a bit different. This describes two triangles are similar means that they have the same shape, but not necessarily the same size. Okay, so in particular, one could be a rescaled version of the other. Okay, and let's draw an example of that. So if we have so we'll take this triangle and we'll scale it in a faithful way. Okay, or we can scale it down similarly. Okay, then these are triangles. These are similar triangles. Something that doesn't work, so if I use one of this, this alters the shape. So this is not similar. Okay? So you have to rescale it in a consistent way using the same scaling factor in all directions. You can't squash it in one direction versus the other. Okay. So now that we've spoken a lot about and just one more point about similarity of triangles. So you do specify the same set of angles in each of these. Okay, so let's say, so this is maybe 3 lines. Okay, so similar triangles have the same set of angles, and this could be called the AAA rule, the angle, angle, angle rule for similarity of triangles. But having the same angles, as is demonstrated in these pictures, does not mean you have congruent triangles, just similar triangles. Okay, now let's talk about compass and straightedge. So a straight edge is about as basic an object as you would expect. It's a tool for making a straight line. Okay, it doesn't have any markings, so you can't make lines of any particular length. Okay. And then a compass, those neat little devices you might have seen at some point. Okay, this is a tool for making a circle. You place one tip at the center and hold it fixed. Then you rotate the other tip around while keeping the length between the tips constant. Okay. And so the reason that these are important for us is that these were kind of thought to be the most reliable tools in ancient Greece. And these are tools for making circles and lines given any, so let's say you have a pair of points, then you can make a line between them. And if you have and you can also make a circle where one is the center and the other is on the circle. Okay, so given 2 points, a straight edge, and let's call this P and Q, a straight edge can make the line segment PQ, and a compass can make the circle with radius PQ centered at P. Okay. So now we can look at compass and straight edge constructions. These are, so the idea here is you're assigned, so you're given a task to construct some figure with specified properties. We want to accomplish it in a finite number of steps, of explicit steps, using only a compass and straight edge. In other words, using only line segments and circles. Okay. So let's see what this looks like in practice. Apologies, I had to change location, but let's pick up where we left off. We'd like to see how these compass and straight edge constructions work in practice. So let's start off with the following example. We're going to bisect a line segment. Okay, so let's start by making ourselves a line segment. Okay, let's make it a little smaller because we might run into some problems. Okay, and we have these 2 points here. Okay, and we want to bisect the line segment in between them. Okay, so there's a neat trick for this. And the idea is to, oopsies. The idea is to draw a circle with center at one and passing through the other, and then vice versa. Okay, and then the resulting points of intersection of these two circles give us a line which will bisect. Let's make this a line which will bisect the line segment we constructed previously. So you notice that at every step, we're making line segments and circles that involve points that are precisely specified by our previous steps. So if we had to write down exactly how this went, we would say first, draw a circle. So our task is to bisect the segment PQ. So first, draw a circle centered at P through Q. And then draw a circle centered at Q through P. Mark the points of intersection as A and B, and then draw the segment AB. Okay, and that segment will bisect our original line segment, and we can just write down these names so that we know exactly what we're talking about. This is, this should be P and Q. And this is A and B. Okay, that's bisecting a line segment. Now let's look at bisecting an angle. Okay, so we want this to apply to any angle we would set up. So let's set up an angle here. Okay, and we're going to try and draw a line segment that cuts this angle in half. Okay, well, our first step will be to draw a circle centered at the origin of the angle and intersecting both of these rays. And this will mark off two equal line segments from the origin until those two red points. So these two lines are equal. Okay. That means that if we draw this line segment, we're looking at an isosceles triangle. And if we bisect this line, okay, and let's grant that we can bisect that line because of having done it earlier, that gives us a bisection of this angle as well. Okay, so let's write down the steps that we did to accomplish the bisection of that angle. So we first draw a circle. So the task is bisect the angle. And you know what? Let's be explicit about this. So we'll have a point here, and let's give it a point here and a point here. So this will be A, B, and C. And so we want to bisect the angle BAC. Okay, so our first step is to mark points on AB and AC in equal distance from A. Okay. And then we'll label those, let's say P and Q. Draw the line segment PQ, and then bisect the line segment, or perpendicular bisector of the line segment PQ. And I didn't actually specify this on the previous slide, but this line is perpendicular to PQ. AB is perpendicular to PQ, so this is actually a perpendicular bisector. Okay. So this line passes through A, bisecting the angle BAC. Okay. And there are probably details of the proof of that I'm leaving out, but that's more for our discussion. Okay. Now we arrive at quite a hard one, which is trisecting a line segment. Okay, and for this, I'm going to assume we can do a few things that we haven't proven yet, but which are not hard to demonstrate. First is draw. Okay, so if you draw a line parallel to a given line through a point. Given point, and draw a circle of radius equal to some other circle centered at a given point. Okay, so those are two things I'm going to assume we can do. And now let's look at the problem. So we want to trisect a line segment. So here's our line segment. We have points, let's call them A and B. And we want to split this into 3. And the way we're going to do this is that we're going to position AB as a line that's crossing from one parallel line to another. So we're going to do that by first, let's pick an arbitrary line. Let's make this gray, and we'll pass this through here. Okay. And I prefer a lighter gray, I think. Okay, and we'll send that to the back. Okay. So this is, we can always draw a line with our straight edge passing through a point. It doesn't really matter what direction that edge is in. Okay. And now we're going to draw a line segment of unspecified length along that line. So let's just say that long. Okay. And now we're going to use circles to repeat that length. Okay, so I started it centered here, and then I brought it back to the original point. So that means that this will give me a line segment of the same length going a step further. And now I can use another circle going back one step to give me a third line segment. Okay, so now I have a line segment with 3 pieces, so we know that these 3 pieces are equal. Okay, and now I'm going to use my ability to draw a parallel line to bring this over here, passing through the point B. So we move this circle over here to be centered at B. And then we continue this line forward. So we have our line segment. Let's make that light blue. Okay, and then there's a fresh circle centered at this intersection point. Okay, where which gives us another line segment, and a final circle centered at that last intersection point, okay, which gives us the third line segment. So it's a line segment split into 3 equal parts, again with the points of intersection, or the points of demarcating the thirds of the line segment marked in blue. Okay, so what do we do now? How do we finish it off? Well, we're going to connect these lines to divide AB into 3. And connect these points. Okay, so because the gray lines are parallel, we know that these green lines are also forced to be parallel, since they're a fixed distance apart on the pair of gray lines. Okay, and since the green lines are parallel, that means we're looking at a set of similar triangles. Okay, and when you have similar triangles, lengths are proportional. So if you have, for instance, if you know that this length is equal to twice this length, or rather, sorry, I should put it this way. If you know that this length is 3 times this length, then that means that in the corresponding sides of the similar triangle, this length should be 3 times that length. And the same goes for each of these pieces. Okay. So that tells us that we've successfully trisected the line segment AB. Okay, but how would we describe this in terms of a procedure? So we would say, start by drawing a line through A, mark a point on that line, make 2 more. So let's make that P. Mark a point P on that line, make 2 more line segments along the line equal to AP. Okay. So in this case, we have P will be given by this point here. Oops. Okay. Draw a line through B parallel to the other line. Mark 3 points going from B, 3 points distance, rather, equal to AP along the line from B. Okay, and then connect the 4 points on, or rather, the 4 pairs of points on the parallel lines. So this is quite a complicated construction, but also quite an interesting one, I think. And this can be generalized to divide a line into any number of segments. So if you want to divide a line into 5 segments, then instead of going out 3 segments on this line, go out 5 segments and just follow the same principles. Okay, so let's briefly talk about what a regular polygon is. A polygon is a shape made of a sequence of points connected by line segments. Okay, so a triangle is a perfect example of that, as is a rectangle or a pentagon, etc. A polygon is regular if every side has the same length. And by side, we mean these line segments. And every angle has the same measure. Okay? So that is called a regular polygon. And these are highly symmetric. You can rotate them so that one point goes to the next point and you've got the same shape back. Okay, well, let's try and build some of these regular polygons. Okay, the first one will be the equilateral triangle. And this one is pretty easy. So we have a point. Let's start with a point A. Okay, so let's say we also have a point B. And we want to build an equilateral triangle that has AB as one of its sides. Okay, well, this is not hard. We draw a circle centered at AB. It's like a circle centered at A going through B, and a circle centered at B going through A. And there is, let's make that a little nicer. Okay, and the resulting point of intersection is an equal distance from both A and B. So that makes it another vertex in an equilateral triangle. Okay, so there's our equilateral triangle. All of the sides are equal, as we just demonstrated, and all of the angles are equal as well. Okay, how about a square? Well, it's a little trickier, so let's start with some line segment AB. Okay, so we'll put our points here. So we want to get a square. So one thing we can do, since we know that the angles of a square are right angles, if we have a line which is perpendicular to AB and passes through A, and similarly another one that passes through B, that will get us most of the way there. Okay, so okay, but an alternative would just be to think about this as living on a circle whose center is the midpoint of this line. And then if we have another perpendicular bisector going through that midpoint, then where that intersects that very same circle will also be corners of the square. So I think that's the approach we'll take. So let's start by doing, oopsies. Circles here and here. Okay, now this line, oops, is a perpendicular bisector to AB, which means that I can put a new circle there, centered here. Oopsies. Which passes through this. Oopsies. One more try. Okay. Oh, that's pretty good. Okay. And then where the perpendicular bisector intersects that circle gives us the remaining corners of our square. Okay, and so we'll have one, two, three, and four. Okay, and that's a square. Okay, how about a regular hexagon? Okay, you'll notice I skipped pentagon. Don't worry, we'll come back to it. Okay, well, let's start again with our edge AB. So we have A here and B here. Okay, so, you know, it's maybe a little too big for the, oops. Let's make it a little smaller. It's going to be a lot of sides. Okay. Now we have A and B. And how can we construct the hexagon? Well, I think the idea of having these edges sit on a circle was useful for us with the square. So let's try and do something similar. A trick that we'll use for the regular hexagon is that if you look at the center of a hexagon and you take the center together with two corners on an edge, those 3 points form an equilateral triangle. So because of that, we can start by constructing an equilateral triangle. Okay, using the approach we already described before. Okay, so here we go. Here's our center. And this is the equilateral triangle. Well, now, if this is the center of the hexagon, it's also the center of the circle that the hexagon is inscribed in. So we can draw that. Okay. So obviously this wasn't a perfect drawing. Say it's approximately like that. And now to make sure that all of the sides are of the same length and that they all sit on this circle, we're just going to draw circles of radius AB centered at each of the points going forward. So, oops. So we have this point is next, and then we can draw another circle centered there, passing through B. So we have another point there. And then we can get another circle, also passing through this point. And that gives us a point here. And we get another circle there. Okay. And these approximately intersect here. Okay. And, you know, humans are error prone, which is why this drawing is not perfect. But we still get a pretty nice picture connecting these green dots. Okay, so that's our approximately regular hexagon. As for the regular pentagon, unfortunately, that is complicated enough that we can't deal with it in this lecture, but we will certainly deal with it in another lecture to be posted soon. Thank you so much for your attention until now.